So since we are out for snow, I'm just going to make a hopefully quick video to run through the notes that you picked up last class and finish the 3.2 notes from last week. So this is the last page of the 3.2 notes. So it ends up, we talked about model scales for the part that we did finish. Unitless scale just means that both quantities have the same unit, so you don't really have to state a unit because it's obvious. A unitless ratio are two quantities with identical units. So again, because it has the same units, then it doesn't need to be stated. All right, we talked about how a model is something that there's a proportion or ratio that represents the difference between the model size and the actual size. Okay, so just using this scenario of a 3-inch frog that is said to be able to jump 60 inches. So the ratio between body length, which is the 3 inches, and the jump distance, which is 60 inches. So 3 inches to 60 inches. And because they have the same unit, then they sort of cancel each other out like in dimensional analysis. And 3 and goes into 60 20 times. So the ratio is 1/20, or you can write it like this. Either way, those mean the same thing. Those are both a way to state a ratio. Is it a unitless ratio? Yes, because both quantities are in inches. Assuming the jump distance is proportional to body length, find an equation. So we did body length over jump distance. So I'm going to do body length over jump distance. Right, and that is equal to 1/20 because that's what we found in part A. So I'm just going to switch that over to some variables. So I'm going to say body length over jump distance equals 1/20. So what I can do is I can cross multiply, which would give me 20 times the body length equals 1 times the jump distance. So that kind of becomes my formula. If I know the body length, I can multiply it by 20 to get the jump distance. If I know the jump distance, then I can divide by 20 and that'll give me the body length. What are the units for this constant of proportionality? Again, it's unitless. Assuming that people can jump like frogs, use your equation to determine how far a 4-foot tall child can jump. So if we use this formula, the jump distance equals 20 times the body length, which is 4, so 80 feet. Remember, this was unitless, and then we have the 4 feet here. So if this is unitless times 4 feet, our answer is going to be in feet. Assuming people can jump like frogs, use your equation to determine how far a 2-meter tall adult can jump. So same thing, jump distance equals 20 times 2 meters would be 40 meters. Alright, so then on the back, finishing up the 3.2 notes, now we assume we have been given a 3-inch frog that can jump 5 feet. So notice we have inches and feet. So with the ratio between body length and jump distance, so it says use the 3 and the 5, but don't convert the units with the first quantity scale to 1. So 3 inches over 5 feet with the second quantity scale to 1. So 3 inches, 5 feet, use the first quantity scale to 1. That's where I was getting lost. Right, so then if you cross multiply, you have 3x equals 5, which leaves you 2x equals divide by 3, 5/3. So that ratio is 1 inch goes for 5/3 feet. Is this unitless? No, because we have two different units. All right, assuming jump distance is proportional to body length, find an equation for this relationship. So body length over jump distance equals 1 over 5/3. So we're just cross multiplying. We have jump distance times 1 equals 5/3 times body length. Assuming people can jump like frogs, use your equation to determine how far a 4-foot tall child can jump. So jump distance equals 5/3 times the 4-foot child. So if you're doing this in your calculator, make sure you put this in parentheses. 5 divided by 3 in parentheses times 4, and you're going to get 80 feet. Last up, assuming people can jump like frogs, use your equation to determine how far a 2-meter tall adult can jump. So it says use 1 meter equals 3.28 feet. So if 1 meter equals 3.28 feet, then 2 meters is 6.56 feet, right? You're just doubling the 1, so you double the 3.28. All right, so it is 6.56 feet times 12 is 78.722 inches. We're just taking we converted the 2 meters to feet, and then we're converting the feet to inches by multiplying by 12, since there's 12 inches in a foot. We have jump distance equals 5/3 times 2 meters. That is the same as 5/3 times the 78.722 inches, because we converted. And again, if you're doing the calculator, make sure that goes in parentheses, and you get 131.20 feet, because the 5/3 was feet over inches, so feet over inches, and then we have inches here, so the inches cancel and you're just left with feet. Alright, so now we're done with that set of notes. The filled in notes are already available in Canvas. Now we're going to tackle the 3.3 notes on rates. Okay, so we're still going to be using some proportions, dimensional analysis from the earlier parts of the chapter. We just want to kind of go over a couple details with big numbers and scientific notation. So if it says million, that equates to 10 to the 6th power. Billion equates to 10 to the 9th power. Trillion, 10 to the 12th power. Every time we go up from million, billion, trillion, we're adding another 3 zeros. So if you were, say, example, 6 million is the same thing as 6 times 10 to the 6th. You could do that in your calculator. So 6 billion would be 6 times 10 to the 9th. 6 trillion is 6 times 10 to the 12th. So whatever number you have before the million, billion, trillion, you can multiply it times the 10 to the appropriate power, because that indicates how many zeros it is in those numbers. Alright, so prescription rates. So this is all going to be about from the same information. In 2011, nearly 14 million monthly prescriptions were written for American adults that were 20 to 39 for ADHD. If there were 82,364,000 adults in this age group, compute the following. So we're using two numbers. We're using the 14 million and the 82,364,000. Okay, and the rate would just be that 14 million over the 82,364,000. So those words that mean numbers behind the actual numbers, we have to include those. So if we convert to scientific notation, that's 14 times 10 to the 6th. 1,000 is just times 10 to the third, right? 1,000 has 3 zeros. So you can, and I want to stress this, you can just type these entire numbers into your calculator. Like you can get in your calculator 14 times 10 to the 6th and get the true number 14 million with all the zeros. And you can type in your calculator 82,364 times 10 to the third, which just is going to put 3 zeros on the end of this number. And then you can divide them. So you do not have to use the shortcuts available with scientific notation, okay? But exponent rules tell us that if we're dividing one number by another, then with the exponents, we can just subtract them. In other words, these 3 tens right here are going to cancel out 3 of these, and we'll just have 3 left. And that just makes it easier to work with smaller numbers. So really, we just have 14 times 10 to the third over 82,364. And it's just fewer numbers. This is just 14 with 3 zeros divided by this, and you get 0.170. What does that mean? It means there's 0.17. I'm going to use script to shortcut for prescriptions. Scripts per adult 20 to 39. That's what we've just determined. That's the rate. Okay, 0.17 prescriptions per adult in this age range. Okay, if we divide the 14 million prescriptions by the rate, prescriptions per adult, from number 1, what are the units? So if we do the 14 million prescriptions divided by prescriptions per adult, then you're going to just be left with the million adults. I'll show you what I mean. So 14 million prescriptions times 1 adult per 0.17 prescriptions. Okay, and that's that dimensional analysis. So the descriptions, they go away, and what's left is going to be million adults. Okay, so the units are million adults 20 to 39, because those are the things that we weren't able to cross out. Okay, all right, and this should equal, it should come back to the 82,364, because you're just using the same numbers from this problem with the answer, so it's just, you're not involving new numbers. So this does equal 82,364 million adults in this age range. Okay, the rate of prescriptions per 100 adults, 20 to 39. So we're going to use the answer from number 1. Okay, so answer from number 1 times 100. Okay, because it's per 100 adults. So 0.17 times 100 just equals 17. So what did that tell us? It's 17 prescriptions per 100 adults, 20 to 39. Okay, so then we're going to do per 1,000 adults. So we're going to take the answer from number 1 times 1,000. So 0.17 times 1,000 gives you 170 prescriptions per 1,000 adults, 20 to 39. How about per 100,000? So still taking that same rate from number 1 times 100,000 gives you 17,000 prescriptions per 100,000 adults in this age group. And then there's no right or wrong answer. What rate do you think is best? I said that it would be the answer out of 100, because that out of 100 means it's a percent. So when you do out of 100, what you're getting is a percent. So your answer for number 3 would tell you 17%, and that's just easier to digest than saying, you know, if you say it's 17,000 per 100,000, that's just harder to sort of figure out like how that matters as much as if you say just a 17%. All right. So then for this one, so some of this is set up with dimensional analysis. That doesn't necessarily mean you have to do it that way. This, how that's set up, it's, you really can just do 5,100 divided by $300 per month, and the dollars are going to cancel. So you're going to do 5,100 divided by 300, the dollars are cancel, and then your unit that you're left with is months. So you don't necessarily have to make it more complicated than that, unless there's a specific reason why you need to be able to set it up in a certain way. So here, it's just multiplying. So it's people times meters squared per person. So the people and the person will cancel, and your final unit will be meters squared. So if you do 400,000 people times 6.2 meters squared per one person, right, then those would cancel. So you're still just doing the calculation, still 400,000 times 6.2. The difference is just what's your unit of your answer, and the people and the person, that's the same unit, that would cancel. You actually get 2,480,000 meters squared, which again, it's million, so you can write that as 2.48 times 10 to the 6 meters squared if you want, like that's the same answer. All right, 20 miles divided by 40 miles per hour, so the miles will cancel and you'll just be left with hours. So you literally can just do 20 divided by 40 and your answer unit will be hours. If you want to set it up with dimensional analysis, it would be 20 miles divided by 40 miles per 1 hour. Now here you got to remember a little math. When you divide by a fraction, you actually turn that into a multiplication problem by flipping the fraction that you're supposed to be dividing by, which works out because with dimensional analysis, that sets you up to cancel those miles. And so that leaves you with just hours. And then it's still going to end up being 20 divided by 40, so it is 0.5 hours. All right, 450 pounds divided by 50 pounds per cubic inch. So you can just do 450 divided by 50, and the pounds will cancel. Your final answer will be in cubic inches. If you set it up as dimensional analysis, it would be 450 pounds divided by 50 pounds per cubic inch. But again, when you divide by a fraction, you change it to multiplication and you flip the thing you're supposed to be dividing by. You're still in the end going to do 450 divided by 50 with a final unit of cubic inches. So 450 divided by 50 is 9, and it would be inches cubed. Okay, we're going to compute a fatality rate per 100,000 people. So the fatality rate would be the number killed divided by the population. So we're going to use this number, and this is population in thousands. That's important. And then whatever it says it wants to be per 100,000 or per person, you get your number for your rate and then you multiply by that. So here it's going to be the number killed divided by number of people in thousands though. So whenever they attach those numerical words to the actual numbers, that has to be involved. Okay, so it's 32,983 divided by 289,562. You can do 10 to the third or just times 1,000. There's not a whole lot of play with scientific notation here because there was nothing to worry about here beyond the number they gave us. So in your calculator, it's 32,983 divided by, it's this number with 3 more zeros. If you don't believe me, actually type that in your calculator. It will be this number with 3 more zeros. Okay, so when you divide that out, you get 1.139. Well, let me backtrack that. In your calculator, it will give you 0.001139. So we talked about how like Excel would change that to scientific notation. When you do scientific notation, you always want the decimal after 1 digit, so it would get moved back here, and we'd have to move it 1, 2, 3, 4 spots. And it's a small number, so this is the same as 1.139 times 10 to the negative 4th power. But we're still not finished because we have to do per 100,000 people. So after we get the rate of drivers killed over the number of people in thousands, we want to take the number and we're going to multiply times 100,000. So it doesn't matter, you know, which form of the number. This is already in your calculator. You're just going to multiply these, and it's going to give you 11.39 per 100,000 people. That's going to be your answer. All right, I'm going to do like one more of these, and then again, the whole notes will be posted so you can look at it. I just want to make sure you had something like an explanation to go with it. Okay, so we have 12.47 motor vehicle deaths per 100,000 drivers times 281,312,000 drivers. Okay, so we've got the 12.47 per 100,000. Per means you're dividing. Okay, and then we want to multiply that. So if we just put this in our calculator, we can get the decimal and then multiply it times this times 3 more zeros. Okay, so you could do that. This divided by 100,000 times this times 1,000. You get the same answer. Okay, I'm going to kind of show you what it looks like though if you do with scientific notation. Alright, so it says times 281,312,000. Okay, so I'm going to rewrite that all as 12.47. 100,000 is 1 zero short of a million, so that's 10 to the 5th times 281,312 times 10 to the 3rd. Okay, so you have the 10 to the 5th and 10 to the 3rd. So these 3 will cancel out 3 of these, and I'll still have 2 left. So it's just working with, you don't have to do it that way, but it's just working with easier numbers. So in my calculator, I'm going to actually do 12.47 times 281,312, and I'm going to divide by 10 squared or 100. And what you should get is 35,079.6 motor vehicle deaths, which you can also write, remember scientific notation, it's 1 digit and then the decimal. And we would have had to move this 1, 2, 3, 4 spots, so times 10 to the 4th. Okay. All right. For this one, it would be this is everything will be posted. This is just same with just working with like 100 million. So 100 million is 1 zero short of a billion. So this would be 10 to the 8th. That was 10 to the 9th. Play around with the numbers. See if you can come up with the right answer, and then compare that to what's on the filled-in notes that are posted. Okay. Here we've got 210 miles. Just rewriting, it's 30 miles per gallon. That's what MPG stands for. Times $2.50 per gallon. So the miles will cancel and the gallons will cancel, and the actual math, we're going to do, you can do it in any order, 210 divided by 30 times 2.5, or you could do 210 times 2.5 and then divide by 30. That part does not matter. So like 210 times 2.5 divided by 30, and you get 1750. The kind of my point is that the dollars is the unit that's left over. All right, and then back here. So I know there'll be some homework questions that come up. Okay, a hose fills a pool at a rate of 4.95 gallons per minute. How many per minute? How many hours will it take to fill an 8,000 gallon pool? So we can do a proportion for this one. 9.45 gallons in 1 minute, right? That was the rate, 9.45 gallons per minute. And we want to know how long is it going to take if we have to fill up 8,000 gallons. Now, it's got to be gallons to minutes, gallons to minutes. So we're going to get our answer. We're going to cross multiply 9.45 x equals 8,000, and then you're going to divide by 9.45, so you should get 846.56. But again, that's in minutes, and the question was how many hours. So we're going to take the number of minutes, and because there are 60 minutes in an hour, we just have to divide by 60, and the answer is 14.11 hours. Okay, if your car gets 26 miles to the gallon, how much does it cost to drive 300 miles when gasoline costs $3.29 per gallon? So there's more than one way to do this, but basically going to figure out how many gallons I need if I can drive 300 miles on 26 gallons, or 26 miles per gallon is my rate. So if I have 300 miles divided by 26 miles per gallon, then the miles is going to cancel, but it's still just 300 divided by 26. That gives me 11.45 gallons. And that's the number of gallons that I need. It's $3.29 per gallon. So that's a total of $37.97. Okay. Candy store sells your favorite candy for $7.99 per pound. I know, like at Fresh Market, I like to go on Tuesdays, Chuck and Chicken Day. Check it out if you don't know about that. But that's a store that you can like you get the little scoop, and you can get as much of that particular candy as you want, and it's a cost per pound. So I find my favorite candy at $7.99 per pound. I fill a bag, but it's not a pound, it's 0.57 pounds. How much is that going to cost me? So again, I can do a proportion. $7.99 per pound is equal to how much if it's 0.57 pounds. So you cross multiply, and this one you would just divide by 1. So when you cross multiply, you get your answer, 4.5543, which translates to $4.55. Okay. What is a better deal? You can buy 12 pounds of flour for $6.72 or 5 pounds for $3.99. So we're going to just figure out what the rate is for each buy. So we've got $6.72 will get us 12 pounds. That's at a rate of 56 cents per pound. Or we can buy for 5 pounds, we can spend $3.99. That's at a rate 0.798 per pound. So the better buy would be to go ahead and get the 12 pounds if it's not something like that you're going to have to throw away. So, tend to think that the bigger quantity should be the better deal, but we like to check because that's not always the case. All right. Lastly, so Dominion Energy charges 12 cents per kilowatt hour of electricity. I don't know if that's the actual charge currently or not. What is the cost of keeping one 60-watt light bulb on for 12 hours each day? If you switch to a 15-watt bulb, how much would you save? All right, so we're going to start with the 60 watts. And it's kilowatt and watt. So just like there's 1,000 meters in 1 kilometer, there's 1,000 watts in 1 kilowatt. So that's where I'm getting that. Okay, just the metric system. All right, so then you can see that the watts cancel, and it's just 60 divided by 1,000. Let me just go ahead and add that in there. Times the 12 hours that we're going to leave this on. So the calculation, we're going to do 60 divided by 1,000 times 12. And we're going to get 0.72 kilowatts per hour. All right, and then it says it's 12 cents for each kilowatt. So it's going to be that value we just got times the 12 cents. So that's our per day cost. And then it says, now we need to look at what is that for an entire year. So it's going to be 0.0864 times 365 days. So the yearly cost of one 60 watt bulb for 12 hours each day is $31.54. Okay, now we have to look at the 15 watts. So we're going to basically repeat. There's still 1,000 watts in a kilowatt. And we're still going to leave it on for 12 hours. So in our calculator, it's going to be, you can do 15 divided by 1,000 times 12, or you can do 15 times 12 divided by 1,000. That part does not matter. That is 18 cents per kilowatt, or kilowatts per hour. Then we're going to take that times the 12 cents that it cost, and this is what we get. That is our 12 hours a day cost. And then we're going to take that times our 365 days to get the yearly cost, and that is $7.884. So $7.88, but they want to know what is the savings. So the savings would be the difference between the 60 watt cost and the 15 watt cost. So we would just subtract $31.54 minus the $7.884, and $23.66 would be our savings in a year. Okay, I hope that helped, and enjoy the snow.